Okay. Sorry Claire and Maggie to interrupt you. Alright, so we'll start with our test conditions. So at this, we're scheduled for Friday over lesson 3 and 4. It's our lesson over recess. It's 70 minutes, so we'll probably have some recess and then start about 10:30. If you've made alternative arrangements, that's absolutely fine. 70 minutes, 54 marks, you get your calculator and you get one A4 page of handwritten notes. Content is just chapter 5, 5A, B, C, D, and then here's the skills that we're going to be assessing as well as the revision resources. Okay, let's turn the page and we'll go through these questions together just to summarise the unit. We have find the exact area bound by the function E. Remember I bought a razor in here the other day? So the function E by itself is just a number. There's no x involved. And so if we have f of x equals E, remember E by itself is E to the power 1, right? Anything by itself is to the power 1. And that is 2.72-ish, right? So on the Cartesian plane, what it would look like, here's x, here's y, and we have the line y equals 2.72. It's a horizontal line at the y value of E of 2.72. Okay, so that's the first part, that's the function f of x. And then we have the function g of x, which is x squared. And that's the parabola that goes through the point of origin. This is the function x squared. And we are asked to find the area between them. Okay, so first we need to know what are these points of intersection. When does f of x equal g of x? When is x squared equal to E? Square root both sides, and we'll have x is plus or minus the square root of E. So square root of 2.72. And we're going to keep it in exact form. Remember, in our test, frequently we have ones that just say evaluate, and then every now and then we say find the exact value. Anytime we have the exact value, we need to keep it in terms of E, in terms of ln, in terms of pi, etc. It means find it without decimals, without using your calculator. So for this integral, we're going to do the integral. Come up here and do it. The area is going to be the integral of the top function, take away the bottom function. So what we have is we have the integral of E, take x squared with regards to x, and the boundary, we're integrating from minus root E to positive root E. Okay. Now remember, E is a number. So when we integrate it, here we have a number that we're going to integrate. And remember, the integral of k is kx. So when we integrate E here, it's going to be E times by x. All right, not to the power of x because it's a number, it's a constant. When we integrate a constant, E or k, we get kx. And then the next one's just pretty straightforward, x to the 3 on 3, from minus root E to root E. Okay, so step 1, step 2, we'll sub in our upper and our lower boundary, so we're going to have E root E, take away root E to the power of 3, on top of 3, take away minus E root E, take away minus root E to the power of 3 on top of 3. Now what's absolutely fascinating about this is I think all of these are going to be like terms. We're going to collect all of them together. And I'll show you why. What we have here is we have E to the power of 3 on 2. All right, it's E to the 1 times E to the half. 1 plus a half is 3 on 2. And then in here we have the square root of E. Square root of E means E to the half, and that's to the power of 3. So we have E to the half to the 3, and we multiply those indices together to get E to the 3 on 2. So what we have here then is we have E to the 3 on 2 from that one, take away a third of E to the 3 on 2. A third because we're dividing it by 3. All right, very good. Okay, so there's that part there. And then we have take away. We've got negative e to the 3 on 2. And then the same thing's going to happen with this one. We're going to have take away. In the bracket here, we have minus root e to the power of 3. Now this means minus e to the half to the power of 3, which means minus e to the 3 on 2. The reason the negative is going to remain is because a negative to the power of an odd number will always be negative. A negative to the power of an even number will always be positive. So the negative remains in the bracket here. We have negative e to the 3 on 2, and we have a third of it again as well because of the 3 there. So just keeping track of your negatives, there's a lot of negatives going on here, right? So that one's still there, that one's still there, and that one's followed through when we've evaluated it. Okay, now we can start to collect it nicely. Now if I have e to the power of 3 on 2, then I take away 1/3 of it, I'm going to be left with 2/3 of e to the 3 on 2. So that's what that collects to. And if you type that in your calculator, my assumption is it will spit it out like that because it can collect some simple ones. Then we have here this negative here is going to distribute in the bracket. And so we can think of it as making every other negative in here positive, right? It's going to go there, which makes it positive e to the 3 on 2. And it's going to come here, which makes that plus negative e to the 3 on 2. Negative a third e to the 3 on 2. All right, so at this stage, they're all going to collect, but here we have e to the 3 on 2, take away a third. That's going to leave us with 2/3 of e to the 3 on 2. And here we have plus 2/3 of e to the 3 on 2. We have 2/3 plus 2/3, that's 4/3 of e to the 3 on top of 2. All right, now that's worked out quite nicely. We sort of did maybe a bit of a longer process when we went from, because another way to think of it is that it's symmetrical about the y-axis, so integrating it from 0 to root e. Cool. All right, so that's our first question. Let's move on to question 2, which is a kinematics question. So we have an acceleration function, which is 2t take away 3. All right, first part. Find v of t given the particle has an initial velocity of 2 meters per second. Well, v of t is the integral of a of t, right? So it's the integral of 2t take 3. We'll integrate this and we'll get t squared take 3t plus c. We also know that the initial velocity is 0. So that means, that means v of, when time is 0, the initial velocity is 2. So 0 squared, take 3 times 0 plus c equals 2. Initially, when time is 0, it's traveling at 2 meters per second. So this gives us c equals 2. And so therefore we've found the value of c, which is 2. We have the whole v of t function exactly. All right, show that the particle is stationary when t equals 1 and t equals 2. Two ways to do this, and I'll show you both because both make sense mathematically. So if it's stationary, it means the velocity is 0. So the first intuitive way might be to go, oh well, v of 1, if I put 1 in, I'm going to have 1 squared take 3 plus 2, which equals 0. So this shows you when time is 1, the velocity is 0. If velocity is 0, it's not moving. How about v of 3? Oh well, we'll have 3 squared take 3 times 3. Sorry, v of 2. 2 squared take 3 times 2 plus 2. Okay, 4 take 6 plus 2 is 0. So that's perfectly suitable. All right, you've shown that it's stationary. And of course, the other way would be to draw its sign diagram, where we have 1 and 2. We have positive A. Now remember, if it's negative, it's going to open downwards. Here we have positive A, which is going to open upwards. So that's the shape that we get for v of t. And because the velocity sign diagram changes sign, it's changing direction. It's a route on the velocity sign diagram, so it's stationary at those points. So that's part B. Part C, find the total distance travelled over the first 3 seconds. So we could draw a motion diagram, right? And that's popped up in practice tests before and so forth. Now, if we look at the graph of what's going on with this function, it looks like this. Here's 1, here's 2. It's coming down and going this way. All right, so that's the velocity time diagram. Now remember that area under a velocity time diagram is going to be the distance travelled. However, we've got a number of intervals we need to consider here. If we just did the integral from 0 to 3 of v of t, this would be the displacement. All right, and that's because it's calculating how far it's moved to the right, take away how far it's moved to the left, and then plus how far it's moved to the right again. Okay? So because it's subtracting, what's going on here is it's moving to the right, positive velocity, then it's moving to the left, negative velocity, and then it's moving to the right. The reason it would calculate displacement is because it's going plus, take away that, plus that component. All right, so it's going to calculate the displacement rather than the distance. So for us to calculate the total distance, we need to consider it as 3 separate intervals. We have the interval from 0 to 1, that's this first part. And then we're going to take away the interval from 1 to 2. We're going to take it away because over that interval, it's below the x-axis, which means it's negative over this region. And then plus the integral from 1 to 3. All right, and now it'd be perfectly suitable for us to type that into our calculator, those 3 separate components. Integral from 0 to 1 of v of t, take the integral from 1 to 2 of v of t plus 2 to 3, sorry, thank you, from 2 to 3. Type that in. You should, yes. I haven't written poorly there. Very poorly.
Yeah.
Although they would accept the final answer. So yeah, it's just better to communicate properly.
Well, I'm not doing it.
All right. So from 0 to 1 of x squared. What does it take? 3x plus 2. That's 5 on 6. And then we have to take away. I'm just going to go ahead of my integral from 1 to 2. Negative 1 on 6. And then plus from 2 to 3. And I've got 5 on 6. So we've got 5 on 6 plus 1 on 6 is 6 on 6, plus 5 on 6 is 11 on 6 units. We're told meters. Meters per second. So meters. 11 on 6 meters is the total distance travelled by considering when it's above, when it has positive velocity, and when it has negative velocity. Now, of course, we could obtain that drawing a motion diagram as well, like I just indicated up here, when it's going right, when it's going left. So both are perfectly suitable ways of obtaining the total distance. Okay, on to question 3. So this is a bit of a problem-solving one. Now, looks like this. We have a polynomial. That's going straight down there. And we have regions A, B, C, nope, C, D, E, F, x-axis, y-axis. Okay, the area of each region is expressed in terms of A, B, C, D, E, F. The functions intersect at x is 0, 2, and 5. So the functions being this line and this curve. So we have there, x is 0 here, x is 2 here where they intersect, and x is 5 here. where they intersect. Evaluate the equation of line is f of x, polynomial is g of x. In terms of a, b, c, d, e, f, evaluate the following definite integrals. Okay, so sorry, we're told the function, the equation of the line, that's f of x, the line is f of x, and the polynomial is g of x. Okay, number one says find the integral from 0 to 2 of f of x. Okay, so f of x is our line. We're integrating from 0 to 2. That's the area under the line. That is going to be b. Now, just as a technicality, it says evaluate the following definite integrals. So it's not relating them directly to area, so we don't need units squared because all we're doing is talking about the value of a definite integral. And that means they wouldn't penalise it. Okay, so that's 0 to 2. How about for b? We have the integral from 0 to 2 of g of x. Okay, so that one's going to be the polynomial. That's this one here. And from 0 to 2, it's going to be region A plus region B. All right, then we have from 2 to 5 of g of x. Okay, so g of x is still our polynomial. Here's 2, and here's 5. All right, and we're just talking about this curve. So what it's going to be is it's going to be positive c, take away e, because e goes below the x-axis, and then plus f. So positive c, take away e, plus f. All right, this one's positive, this one's negative because it's below, and this one's positive because it's above. Very good. Okay, part D, the integral from 0 to 2 of g of x, take f of x. Okay, here's 0, here's 2, g of x is our curve, take away f of x, we're just left with region A. Alright, so we know from 0 to 2, we're subtracting that region, so we're just left with A. And then we have from 0 to 5, this will be a couple of marks this one, from 0 to 5, f of x, take away g of x. Okay, here's 0, here's 5. F of x is our line. Alright, so if we're doing f of x, take away g of x. Alright, over this interval, alright, from 0 to 2, if we're doing f of x, take away g of x, we're going to have negative a. Alright, over this interval, alright, we have f of x, take away g of x, we're just going to be left with d plus e. Alright, because that take away that region, that's going to disappear, and that take away that region, that's going to disappear. We're just left with minus a plus d plus e. Alright, how do we go with that last one? Do we want a bit more explanation or? Yep, so what's going on with the last one here? Let's break it up into intervals. Let's just think about from 0 to 2 first. And we're doing, normally, if we were doing g of x take f of x, that would give us region A, okay? However, so if we were doing, and that's what we got in this one, g of x take f of x is region A. So one of the properties of integrals is that if we have the negative of an integral, like watch what I do here, okay, if we distribute that negative, we would have negative g of x plus f of x, which is f of x take g of x, okay? So, notice how here we have that equals a, therefore if we put a negative in front of it, it's going to equal negative a. So that's one way we can think about why the first region is negative. It's also because normally we would do the top function take the bottom function. In this instance, we're doing the bottom function take the top function, so the resultant area is going to be negative. Okay, when we talk about the second region, if we're doing the top function, take away the bottom function, the only part we're going to have is this part. It's the area between them. So for the second part, for the second component from 2 to 5, it's just d plus e. because it's the area between f of x and g of x. We're not considering c in that calculation. All right, so that's a bit of a summary for the unit so far. Any big questions from what we've gone through here? Very good.